Today we're going to talk about section 2.1, and we're given this problem. It says a stone released from a state of rest falls to the earth. Estimate the instantaneous velocity at t equals 0.8 seconds. So to do that, we're going to look at this equation, and to find the velocity, we're going to look at the change in position divided by the change in time. So since this is our target, we're going to look at different time periods. So when I calculate my first delta S, I'm going to do 0.8, and then I'm going to move over just 0.81 and do it like that. So I'm going to take this, I'm going to plug in 0.81 to this equation, and then plug in 0.8 to this equation, subtract those. That will be my change in distance. And then for time, we're just going to get 0.81 minus 0.8. Now, if we do that, we're going to end up with 0.07889 divided by 0.01. And when we do that, we end up with 7.889. And that's measured in meters per second. Now, I'm not going to go through the calculation, but what we're going to do after this is we're going to cut that distance in half. So the next one we're going to look at would be and so on. Then we cut that in half, cut that in half, cut that in half. And if we do that, you can see the numbers. So we start with 7.889, and then we'll get 7.8645 for this one. And then if we keep doing that, we're going to get 7.8405, and then 7.84024, and then 7.84000. I think that's 4 zeros, and then a 5. So what we see is as we make our distance from the initial velocity that we're looking at, we're getting closer and closer to 7.84 meters per second. And so that's a good estimate for the instantaneous velocity for this problem. All right, example 2. So we're given a formula. Provides a good approximation to the speed of sound, v. So v is the speed of sound. Okay, in dry air, in meters per second, as a function of air temperature, T. So T is air temperature. And that's in Kelvin. Estimate the instantaneous rate of change of V with respect to T when T equals 273 Kelvin. What are the units of this rate? Okay, now we're going to approach this similarly. So I don't really want to go through all of this by hand, but let's just look at the one that the book does, that they go through. And so we're going to do the velocity plugging in that initial so we're doing like half a Kelvin away. We're going to drop that down. And 273 minus 272.5. Okay, so if we do this, if we take 273, plug it in here, and then we take 272.5, plug it in here, subtract those, and then we divide it by this difference, we're going to end up with this. Now, you can look at the tables in the book, or you can look at the graphs that are provided on the sheet below. You'll notice that as we make this smaller and smaller, we'll be getting numbers like this. And so it's safe to say that 0.605 is what we're getting closer and closer to. So let's read the question one more time. So it says, estimate the instantaneous rate of change of V with respect to T when we have this as our temperature. So this would be our instantaneous rate of change of V. And then it says, what are the units for this rate? So this is going to be meters per second per Kelvin. Because the top is velocity, so that's meters per second. The bottom is Kelvin, so we have like meters per second per Kelvin is one way we could look at that. If you have additional questions, please come to Math Lab. Until then, calculator.